So, waves and sound. So this unit is about waves. So we're going to introduce waves, and we're going to talk about the different properties of waves, different types of waves and stuff like that. We're going to talk about waves in general. But then, as we progress into the unit, we're going to focus specifically on sound waves. And then our next unit is going to focus on light waves. So, to start us off with, it gives us a couple of definitions. It says, okay, what is a wave? Well, a wave can be described as a disturbance that travels through a medium from one location to another. So it goes from point A to point B, and it's some sort of repeating disturbance. Some waves require a medium to travel. These are called mechanical waves, and media can be solids, liquids, or gases. And this is the substance, the material that carries the waves. Some can be good carriers, and some are not so good. Okay, so there's some definitions for you. It gives you a definition of mechanical waves, gives you a definition of media, and gives you a definition of a wave in general. So while you're digesting that, I want you guys to realize something. So we are in physics class. Physics is the study of matter and energy. That is the definition of physics. So we started the year off talking about matter and how matter moved, and we learned about velocity, acceleration, displacement, we learned about projectile motion and all of these different things. That's really just how matter moved from one place to another. Then starting with this semester, we started learning about energy. What is energy? We didn't start talking about what matter was, because it's essentially what your chemistry class covers. So you should have known what matter was, and when you come in here, we talked about how it moves. Then we started talking about energy, what it is. We talked about kinetic energy, potential energy. Now we're going to talk about how that energy moves. And it moves using waves. So it says a wave can be described as a disturbance that travels from one location to another through a medium. So medium, as it says right there, it can be literally anything. It's a solid, it's a liquid, it's a gas. It's just something that the wave travels through. So for instance, I am communicating to you guys right now using a sound wave. You can hear my voice speaking to you. It is a sound wave. It is traveling from one place to another. In this case, it's going from my mouth to your ear. And it is traveling through the air being the media that is filling this room. However, some of you have gone swimming before, yes? Can you talk underwater? Yes. Is it easy to understand people when they talk underwater? No. And it turns out the main reason why you have such difficulty hearing or speaking underwater actually has to do with the fact that, well, water is a different medium than air. As a result, things are different. The wave travels differently. More specifically, the wave travels a lot faster. It travels almost 5 times faster in water than it does in air. And so things are different, and speaking is basically the same, but hearing is a lot different when the things are going so much faster. It's harder for your brain to process because it's just not used to it. Okay? So a wave is just any disturbance that travels from point A to point B through medium. Mechanical waves require media. If it requires media, it's a mechanical wave. If it doesn't require media, it's not a mechanical wave. So a good example of a mechanical wave would be sound. A good example of a non-mechanical wave would be light. So for instance, you can see the light from the sun. Can you hear the sun? No, because as the saying goes, in space, no one can hear you scream. Because space is a vacuum, it essentially doesn't have a medium, therefore mechanical waves can't travel through it. You can't scream in space because there's no media there. Looks really off. cannon, and it pulls by, shoots a little compression of air. So this is essentially a wave that is traveling. It's a disturbance going from point A to point B, traveling through this medium of air. Make sense? It's kind of intense. Not the eyes. It technically has a sight on it, but it's way off. So, the whole point here is that all waves transmit energy. That is the point, is they're trying to get energy from point A to point B. Right? That is the point. Some you can see, some you can't. You know, for example, sound and light, they're very common. But don't forget other waves, like ocean waves, water waves in general. Those are wave types. What's really nice is that we already know Newton's laws and the laws of conservation of energy and momentum. All of that still applies to waves. We don't have to relearn them. They're the same things that we learned last semester, assuming that you learned them. So they govern the behavior of waves as well as particles. It says that there's a demo here. I'm going to wait a little bit until we talk about frequency to actually do that demo, because it makes more sense now. Yes. So do you have any questions thus far? All right. So this slide is actually pretty heavy on information. So on this slide, it gives you the two basic types of waves. You see on top we have a transverse wave, and then underneath that we have a longitudinal wave. So it gives you the pictures and it tells you the definitions, and then it also labels the parts. So you should be expecting that I could ask you questions on any of these things. So let's go ahead and talk about it. So it says transverse wave. It's the one on top here in the picture. And for transverse waves, we call it a transverse wave because the particle, the media, travels perpendicular to the direction of the wave. Okay? Longitudinal wave, the one you see on the bottom, we call it longitudinal because the particle moves parallel to the direction of the wave. And so this is how they look. But this is kind of like a still picture, because the deal is a wave is an object it's energy moving from one place to another. And because it's always moving, it's kind of hard to see because it's moving. So essentially this is like what a still picture could look like of these two types of waves. So we'll start with the top one when we're talking about the type. So it says crest, trough, height, amplitude, wavelength. What do you think wavelength means? How long the wave is, like the length of the wave, physically, from one point to another. Now the thing you have to be careful with when it comes to the wavelength is you want to measure from one part of the wave to the same part on the next wave. So here in the picture you can see that it's measured from the top of the wave, or the crest, to the next crest, right? And it doesn't really matter where you measure it, just as long as you go from the start of one wave to the start of the next wave. And since they're always kind of continuous, it doesn't really have a start. So just one point of the wave to the same point on the next wave. And then height is pretty easy. What do you think height means? Yeah, from the bottom to the top. It's just the height of the wave. If you were standing on the ocean and you saw these waves coming at you, you could easily measure the height of the wave. Does that make sense? Simply from the bottom, the lowest point, to the highest point. That's the height. Now, amplitude is a little bit trickier. Amplitude is half your height. So if you know the height, the amplitude is easy to find. Amplitude is technically the distance from the equilibrium position up or the equilibrium position down. So you can imagine if we're talking about like a water wave or an ocean wave, you have a flat surface, and then that would be your equilibrium position, and then the height would be from bottom to top, or amplitude would be half of that. Amplitude's kind of hard to measure in reality, because I don't know if you've ever been to the ocean, but there's a bunch of waves. Do you ever see the ocean just like a flat palm? It happens, it's just not very common. So finding the amplitude would be difficult, but finding the height is easy, and so you just cut the height in half to find the amplitude. I say this because it's going to be a lot easier to find the height, but the amplitude is more useful for physical calculations, because we can use the amplitude, inside of an equation to actually tell us how much energy is being transmitted. The equation's a little complex because it has to do, like the density and whatever medium it's moving through and all this other stuff. So we're not really going to look at that equation. But essentially, if scientists wanted to find the energy in a wave, it has a lot more to do with the amplitude than the height or anything else. And then we have the last two parts on our transverse wave, the crest and the trough. So first of all, can you all say the word trough? Trough. It's spelled like that. I want to point that out because the English language is difficult. And most of you have probably heard of the word trough, but you may not have been able to spell it. Trough simply means the bottom, the lowest point of the wave, and crest means the top, or the highest point of the wave. Have you all heard the word crest before? Where? Toothpaste? Bahari Crest toothpaste? Why do you think that they call crest toothpaste crest? What do you think that's supposed to mean? It's top. It's best. It's a crest. You ever heard of trough toothpaste? No, and you're not going to, because what would that be? It would be the worst toothpaste you could possibly buy. And keep in mind, like, brushing your teeth with water would be like your equilibrium position. So trough toothpaste would be real bad. Okay? So yeah, you're not going to find trough toothpaste. But the top and the bottom, the crest and the trough. Everybody okay with that? And so those are our parts. And so you should be able to expect, like on a quiz or a test, I might give you a picture of the transverse wave and remove all of these words and just put letters in their spots and be like, hey, what is this thing down here at the bottom? Or where is the trough? You're like, oh, that's a B, or whatever. So you should be able to pick that out. They're pretty simple. Do you have any questions about the transverse wave at this moment? All right, well, let's talk about longitudinal wave then. So longitudinal, it says it moves parallel, and it has a wavelength. Again, a wavelength is still measured from one point of the wave to the same point on the next wave. So there you can see that it's measured with a compression to compression. But then it would technically also have what we would consider a height, or the maximum point of vibration, and an amplitude, although those are a lot harder to distinguish on a longitudinal wave, so we're not going to deal with all that, which is why you don't see them labeled there. But technically they would have an equivalent on this wave as well as the transverse. But we have the two parts. Instead of crest and trough, we have a compression and a rarefaction. So rarefaction is where the particles have spread out. There's less density there. And compression is where they're all squished together. So here's the deal. These are all the parts. These are the two basic types of waves. Now, some things like an ocean wave is actually a combination of both of these. But in the end, what makes a wave, well, there's several things. But in particular, when it moves through a medium, it disturbs it, right? It pushes these particles back and forth like you just saw the air cannon do. But it doesn't really take the particles anywhere. In the end, the particles will get shoved in one direction or another, but then after the energy passes through, the particles will move back to where they were. Okay? And so that's one of the things that makes a wave is it has this disturbance that passes through it, but in the end, the particles will return to how they were before. So keep that in mind. And when you're looking at these different things here about, longitudinal wave, compression waves, we're also talking about how These particles move, but it mentioned there right in the definition, it says particle moves temporarily in a direction perpendicular to the wave, and particles move temporarily parallel to the wave. So that's a little harder to see. I mean, it's got, on the drawing here, it's trying to show you what it looks like. So here, this is a bit more of an animated thing here. And so at this website, you can see that on top we have a longitudinal wave, right? So this is a compression and rarefaction. Do you see how they're labeled as they travel along here? Like compression and rarefaction. So the compression and rarefaction are the wave parts. Like literally you can watch this compression and just like trace it go through the whole wave. Y'all see that? But the particles, these dots, you know, it pointed out some of them red, they move back and forth. Do they actually go anywhere? No. And so this is what makes a wave a wave. The energy is traveling through this physical medium, but the particles kind of oscillate, but they don't go anywhere. Okay? So the energy travels through the particles, not the particles. Okay? And so a good example of a longitudinal wave is a sound wave. Okay? So for example, when I breathe out, the air comes out of my lungs, comes through my vocal cords, through my throat, and out into this room for you guys to hear. I think we can all agree that I'm physically breathing in material and physically breathing out material. Okay? But the actual sound wave itself is created, you know, as you see here on the board. Let me ask you a question. The physical matter, like the physical air that I'm breathing in and out, that's coming out of my mouth right now as I speak, is this the same air that's going into your ears right now? No. Could it be? Possibly, but it's not. Okay? And it's easily proved because have you ever had somebody breathe air into your ear? Like you ever had somebody come up and whisper into your ear and you feel their hot, moist breath and you think that's disgusting? Well, yes, that's because the air is actually coming out of their mouth into your ear. Is that what is occurring right now as I'm speaking to you? No. Because what's happening is the air comes out of my mouth and it hits the air in front of it. It's just here in the room, which compresses it, and then it shoves those other molecules out a little bit, and then they get shoved into molecules in front of them, and so on and so forth, and these compressions and rarefactions travel out from my mouth to your ears. So the actual material coming out of my mouth is not going in your ears. So that's number one. But number two, it's happening rather quickly. When I speak, no matter where I am in this room, it reaches all of your ears at about the same time. The speed of the wave, as we'll see in a second, depends on the media. And the speed for sound in this room is about 340 meters per second, or about 760 miles per hour. This room is not that big. If something's traveling 700 miles an hour, it can pretty much get anywhere in this room almost instantaneously, because the room is not that big. Does that make sense? But sound travels as a compression or longitudinal wave. So here is an example of a transverse wave that goes up and down. And so again, you can see that the energy, you know, flows through. You can watch the little pieces travel along. So it's an energy flowing through it. But the actual molecules are moving up and down, but they're not really going anywhere. And so if you're looking, if we're looking at these top two, like I said, ocean waves are just a combination of these two. Hopefully you can see in both of these examples, the energy goes from the, just from y'all's perspective, goes from the left side of the screen to the right side of the screen. Do y'all see that? The wave is traveling from left to right. But the particles in the longitudinal wave are physically also traveling left to right. That's why it's called a longitudinal wave. Whereas the transverse wave, the particles are moving up and down and perpendicular to the direction of travel. So what makes a transverse wave is the particles move perpendicular to the direction of travel, and a longitudinal, the particles move parallel, or in the same direction. Can y'all see that? Hopefully you can see that. All right. So, up here it gives us, it says speed or velocity is calculated as displacement over time or distance divided by time. And here's the deal. Is that a new formula? No. It is literally the first formula I gave you this year, back in August. So, you can write it down if you need, but it's an old formula at this point, because that's how we learned to calculate velocity back in the day. And we can still do that. We can still do the distance that the wave travels divided by the time over which it travels and find the speed of the wave. Okay? And it says right there, the speed is only dependent on the medium. I'm going to say it again and again. The speed depends on the medium. The medium gets to choose what speed the wave travels. Because the particles of the media, how fast or slow they can move, is what transmits the wave. And speed of sound and air, like it says, about 760 miles per hour. It's almost 5 times faster in water. Why is it faster in water? Well, because the water molecules are closer together than they are in the air. And since sound is a mechanical wave, it wants these things to be closer together. And it travels even faster in a solid. So speed depends on the medium. That's it. If you see a question that asks you about the speed of the wave, it depends on the medium. Okay? And so if you have a wave traveling through the medium, you can simply find the distance it travels or which time it travels in that medium. The distance divided by time, and boom, you know the speed. It's very simple. It gives you the definition of amplitude and wavelength here, because, well, they didn't fit on the last slide. So if you didn't get my definition from what I said orally, well, there they are on the screen. So you don't have any questions about that. All right, so here this talks about time period and frequency. This is why I was saving the speaker for. So it says right there, the definition of time period is the time it takes for the wave to complete one cycle or oscillation, and frequency is the number of wave cycles per second. So let's think of a simple example before we get into actual frequencies. So for example, have you ever swung on a swing? Or at least watched somebody swing? They go back and forth, right? Let's imagine a person swinging back and forth on a swing. Well, if you were to get a stopwatch out while you watch them swing back and forth, could you start the stopwatch, let's say when they're at the back, then they swing forward, and they come all the way back, and you stop your stopwatch. Could you do that? What would that number be? Could be what? Okay, could be 2 seconds, but my real question is like, what does that mean? What does this 2 seconds mean? It's the time period. It's how long it took them to swing, and it could definitely take 2 seconds. Does that make sense? So you go, I timed it. That was the time period of one swing. Now here's the deal. If you time them for 2 seconds, is that how long they were on the swing? No, they could be on the swing 15 minutes, but it only takes 2 seconds for them to swing once. You all see the difference there? So we have little t, which is how long they've been on the swing, and we have big T, the time period, is how long it takes them to swing back and forth once. You all see the difference between those two numbers? Because they're both technically a time, but one is a time period, how long it takes for the cycle to complete. Now, what does that have to do with frequency? Well, frequency is the number of wave cycles per second. So if it took them 2 seconds to do a full swing, the frequency of that swing would be 1/2. Because in 1 second, the kid would only swing half of a full cycle, because it takes 2 seconds for the whole wave. Does that make sense? So they're inverses of each other, and the formulas are right there. So if you know the time period, you can do 1 over the time period to find the frequency, and if you know the frequency, you can do 1 over the frequency to find the time period. Now, the reason why we introduced frequency, first of all, frequency has units of hertz, which means per second, is because, the reason why we introduced this frequency thing is because, you know, if it takes the kid 2 seconds to to swing once, that's an easy thing to time. You can sit there and you can time it. But what if the kid was swinging really fast? Is it possible for them to swing fast enough that you couldn't time them? Well, probably not on a swing. But what if it was something else? So for instance, I have this speaker up here. Do you all see my speaker? So here's my speaker. I'm going to turn it on. And I have it set now to 1 hertz, or 1 cycle per second. So let me turn it up. And there it is. You all see the speaker? As it moves back and forth. So it's just like the kid on the swing. It starts here, and so we're going from back. It goes from back to neutral, all the way forward to neutral again, all the way back. You all see that? So going back and forth, and it's taking it 1 cycle per second. So it has a time period of 1, and it has a frequency of 1. All right? Now, I could theoretically make this thing slower, right? I can't on this physical thing, but theoretically, I could go slower than 1 per second, right? I could go with a frequency of, say, 2, a time period of 2, which would have a frequency of 1/2, which means it would be going a lot slower than this. But what would it look like if I made it go faster? Well, here, this has a frequency of 2. So it's doing 2 cycles per second. Now you could probably count the number of cycles per second there, right? So to find the time period would be to start a stopwatch when it's all the way back. It'll start here, it comes back, you stop it, right? But the frequency is just goes, okay, typically the way you would measure frequency is you would observe this thing for like 10 seconds or 30 seconds and just count the number of times it moves. 1, 2, 4, 5, 6, 7, 8, 9, 10. And then I would take that and I would divide by the time that I did it in, and I would find the frequency. Does that make sense? So time period and frequency are trying to talk about the same thing, but sometimes it's easier to talk about the time period. Sometimes it's easier to talk about the frequency. If you had a kid on a big old swing, it might take them, let's say, 10 seconds to swing the whole thing. If it takes them 10 seconds, their frequency would be, well, 0.1. And that's a silly number, but you can easily just watch the kid swing back and forth for 10 seconds. But what if it's happening fast, like really fast? Like this is at 2. Here, I'm going to move it up to 10. Can you count 10 of those happening every second? Not really. And here's the fun fact. What is this thing? It's a speaker. Do you hear anything? It's because it's too low of a frequency. Humans can hear between about 20 and 20,000 hertz in terms of the frequency. 20 being the lowest, 20,000 being the highest. Now, how much you can actually hear depends on 2 things. Number 1, your genetics. Some people can simply just hear better than others. And number 2, how much you've damaged your ears. That's it. So, nobody can hear this low. But some people can theoretically hear like 20 hertz, so. Now I can hear this because I'm really close. Y'all may not be able to hear it out there in the classroom. But could you possibly try to count 20 of those happening every second? No. But let me go up a little bit higher. This is 120. There's 120 oscillations per second. There's no way I can count this, and there's no way I could possibly try to time how long it takes one of these to happen. It would be 1/120th of a second. Does this tone sound high or low to you? There's a nice 240 for you. for you. So I want you guys to understand that when you talk about frequency or time period, they're really talking about the same thing. But whether you choose frequency or time period just kind of depends. Because, you know, if that has a frequency of 440 hertz, that would be having a time period of 1 over 440, which is basically going to be impossible for you to measure. Okay? So again, time period and frequency, they're essentially inverses of each other. Are we okay with that? All right. So here on this slide, it talks about period, frequency, and wavelength. So the speed of the wave depends on the medium. That's it. The frequency of the wave depends on the source. Like you guys just heard that speaker there. As I fiddled with those knobs, it changed the frequency, which changed what you heard. So in sound, frequency is related to what? What do you call that? What were you just hearing as I changed that speaker? What's it called? When you change frequencies of sound waves, they're called what? What am I changing? Pitch. A change in pitch is a change in frequency for sound. For light or electromagnetic waves, if I change the frequency, it doesn't change pitch because light doesn't make a sound. But it does change the color. Different colors have different frequencies. So low frequencies for sound are low notes or low pitches, and high frequencies for sounds are high pitches. Right? For colors, do y'all see my kite here? For colors, low frequencies are your red, and they get higher and higher frequencies until you get up to your violet. Now these colors here, the colors of the rainbow, are not the only pieces of light. They're just the only ones that we can see. And so as you change your frequency for light, it changes the color of the wave that you see. So the frequency depends on the source. The speed depends on the medium. The wavelength is a result of those two things. So how long or short the wave is depends on both the speed it's traveling at and the frequency that it was generated at. So for example, I am speaking to you guys right now. Because I am speaking, I get to dictate the pitch at which I speak to you. So the volume has more to do with the amplitude or the energy in the wave. I'm speaking to you guys at a decibel level now of approximately 90 decibels. This is not the level I normally use to communicate. Normally I speak at about this level. This level is about 70 decibels. That is amplitude. Don't confuse that with pitch. If I change my pitch or my frequency of my voice, again, I am the source of the wave. I can change the frequency of my voice because I am the source of the wave. Make sense? The source dictates the frequency, the speed is dictated by the medium, and the wavelength, what you see here, is a result of those two things interacting. So here, on this slide, it gives us the wave equation. Typically, I'm going to give it to you as V equals F lambda, which is the first version you see there. So remember, it's the triangle. We've dealt with them before. It's just one equation, so V equals F lambda, but I can solve for F, or I can solve for lambda, or I can solve for V. So that's V equals F lambda, and that's the second, or technically third equation I've given you today. So this is the wave equation. I gave you, T equals 1 over F. That's an equation, but I also gave you V equals F lambda, V equals distance over time, which I sort of don't count because you guys, we've had that equation for a while. But I've given you technically 3 different equations in these notes. So do y'all have any questions about these equations? Well, here's a question. I give you all a second to try this. A sound wave is produced by a clock chime heard 515 meters away, 1.5 seconds later. What is the speed of the sound of the clock chime's air? The sound wave has this frequency, what's its period, and what's its wavelength. So I'll give you a second. So what y'all think? It says, what is the speed of sound at the clock chimes there? Did y'all get it? What y'all get? Well, let's write down what we know and what we're looking for. So it gives us a total of 3 numbers. So it gives us the distance is 515 meters. And the time, it says 1.5 seconds. And then it says a frequency of 436 hertz. Okay. And it asks, the first thing it says, what's the speed of sound of the clock chimes there? So if this was the clock, and you were, let's say, 515 meters away, so let's assume that you were down here. Here you are. So the clock is 515 meters away. Does that make sense? Like that is this distance. So you have a distance, you have a time. Can you find the speed from that? Good. So we use our formula V equals distance divided by time, 0 t. The distance is 515. The time is 1.5 seconds. So you should arrive at an answer of about 343 meters per second. Everybody okay with that? Now, it says the sound wave has a frequency of 436, what's its period, and then what's its wavelength. So it should be noted that this is the distance. This 515 is the distance from you to the clock. But there's going to be a bunch of waves between here and there. Okay? So that's why we use different symbols for wavelength and for time and time period, because like a little t indicates the time it took to go from here to there. That's little t. Big T is the time of one cycle. So like big T on this drawing would be the time to go from, say, the top of this wave to the top of the next wave. That's like time period. Y'all see that? Whereas like this distance from here to there, again, is just a distance, d. But the wavelength is, again, from here to there. And we use not a L, or as you saw on the last slide, we use a lambda. Looks like an upside down slide. Because that's the Greek because the thing is, they're both lengths, they're both times, but one is specifically talking about how far this one wave is, or how much time it takes that one wave to occur versus how far it actually went. You know, again, it's like the kid on the swing. Like, they can swing for 15 minutes. It doesn't mean it takes the swing 15 minutes to swing once. That'd be a ridiculous swing. So just kind of keep that in mind. So we want to find the time period from the frequency. So, well, we know the frequency. So the time period is 1 over f. So we do 1 over 436. And so your time period comes out to be, what is that, 0.00 like 23 something seconds. So if you're getting 436 waves per second, well, it's going to take a very small fraction of time for one wave to occur. Make sense? And then last but not least, it asks you to find the wavelength. And so if V equals F lambda, for the last slide, lambda would equal V over F. So all we have to do is take this speed of 343.3 and divide by a frequency of 436. And we get a wavelength of like 0.78 for this particular problem, which literally would be about this long. Does that make sense? So again, in this set of notes here, I've technically given you 3 formulas. I gave you velocity as distance over time. I gave you time period as one of the frequency, and I gave you V over F lambda. So the 2 written in black are, I would say, new formulas. The one written in red is old. But again, the old stuff never really goes away in this class. Do you have any questions about this before I move on? All right. So this brings up Doppler shift. So the Doppler shift is, as it says right there, or Doppler effect. I kind of use the words interchangeably, and I shouldn't, but I'm not going to get detailed enough that it makes a difference. But yes, there is a difference there. So it says, the apparent change of pitch, or frequency, due to the movement of a source or observer is called the Doppler shift, or Doppler effect. Okay, so what does that mean? How does that change something? So, okay. Most of you have probably never heard of the Doppler shift, Doppler effect, but you've probably heard of Doppler radar, right? Well, we're about to explain that. We're also about to explain this stuff here it says about planes and trains and sirens and all that. So let me bring up a whiteboard here to kind of explain what's going on. So let's think about this. So hypothetically, let's assume that this whiteboard is a flat, undisturbed water surface, okay? And on that surface, we have a bug. See my bug? And the bug is just sitting there, nothing's happening. But let's say the bug just starts to bob up and down. Could it do that? Yeah, it could do that. But when it does that, it's going to disturb the water surface. And it's going to create ripples. And if the bug is just sitting there, it will look like concentric circles around the bug. And so on. Does that make sense? So the bug is just sitting there creating these ripples. So it looks like, you know, when you throw a rock in a pond, you see it ripple outward. Or it's going to make, you know, kind of like transverse waves on water. And so you can imagine that these rings here, the things I've physically drawn, let's say those are the crests, and the troughs would be the blank space in between. Are you okay with my drawing? So that's how it would look if the bug just sits there. That's essentially what's happening when I'm just standing here and these waves are emanating out of my mouth. They're just spreading out all directions in 3 dimensions. So this is like a circle, but really you should think more like a sphere in 3-dimensional space. What would happen if the bug started to move? Well, let's say that the bug starts to move this way. So let's say that it's over here now. Well, if the bug is moving in this direction, well, it's going to make a wave fairly recently, right? so its most recent wave will be right by the bug. Does that make sense? But earlier, it was back here, right? It was back here earlier. So when it was back here, it made a wave too, okay? But this wave would be centered at this point right here, okay? And because it was made earlier, it's had more time to expand out into space. So what ends up happening here is you have the second circle that, I don't know what that is. So that's a circle centered on the previous dot. Okay? So if I go back to a third spot here, this thing would have a wave centered maybe here. But it's centered on this dot here. You all see that? Then I can go back, let's say I go back one more. It'd be way off my board, but what you can see here happening is that the wave is getting, do you see how it's closer together here at this spot, and it's farther apart back here? That is the Doppler shift. It's a change in apparent frequency from a source or observer moving. So if this bug is coming towards you, it makes sense because the bug is moving with its own speed and the wave has its own speed. So the wave ends up with its speed because the wave speed is dictated by the medium. But let's say he's on water here. Let's say the wave speed is 10 meters per second. Well, the bug probably can't move 10 meters per second. It's like 20 miles an hour. The bug can't move that fast. But let's say the bug is moving, 3 or 4. Well, it's going to create its next wave closer to the wave that's already there. And so they end up getting bunched up in one direction. But behind the bug, since it's moving away from you, it's creating a wave, let's say it's making 1 wave per second, that's its frequency. It's going to take longer for these waves to get to you because it's creating them farther away from you. And so this is the Doppler shift, or Doppler effect, is that it's an apparent change in frequency because the object is moving. And it could be the source or it could be the observer. In this case, I'm making it the source. So, what does that have to do with this? Well, here, as this bug moves along, can y'all see how it gets all bunched up in the front and it's further away in the back? Well, the wave that you would see kind of depends on if it's a water wave, light wave, sound wave. For example, with a sound wave, a great example of this bunching up is what happens when a plane, train, or car goes by you and you're stationary. So you're stationary, you're not moving. But if you've ever watched race cars on TV, you can watch them, and when they have the camera inside the car, you're getting the sound of the engine. It's just running along. But if you watch it when the camera's on the start-finish line, is that what you hear as the car goes by? What do you hear? Meow. Yeah, you hear meow, meow, meow. That's the Doppler shifter effect, because as it comes towards you, the waves are closer together, so it gives you a higher pitch, a higher frequency. It's mee. But then when it goes right in front of you, you get the actual tone of the car, the mee, and then it goes past you, and it's a lower pitch, a lower frequency, because there's less there. So it goes meow, 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 right? And the same thing happens like with a train horn, when it like blows its horn as it goes by, it's like, because it's a apparent change, because you hear it. You're like, that changed pitch. Now in reality, did the train horn change pitch? No, the car engine didn't change pitch. That's just what it is. But it sounds like it did. But here's the interesting thing. We can do these for any type of waves. Water waves, sound waves, light waves. But what's interesting is that, let's reverse the thing. Let's say that the source of the wave is me and you go by. Well, the same thing would happen. If you're coming towards me, the waves would be closer together, and if you're going away from me, the waves would be further apart. What's interesting is this Doppler shift, or Doppler effect, is how we measure a lot of things. So for example, we can send up radar waves, or light waves, into the clouds, then bounce off the clouds and come back. If the clouds are not moving, when the waves bounce, they come back at the same speed we sent them. There's no change in the frequency. But let's say the cloud is coming towards us, and you send this wave up, it will bounce back at a higher frequency. And we can measure that difference in frequency, and we can calculate the speed of the cloud. And that is how Doppler radar works. is that we send these radar waves up, they bounce off the cloud, they come back, and we can calculate the speed and the direction that they're moving in. That's how the radar works. And matter of fact, that's actually how like police radar works. When they use the radar gun to figure out how fast you're going, or their laser gun, they send out light waves at a certain frequency, they bounce off your car, and again, if your car is not moving, they come back at the same frequency. You have a zero speed. But if you're moving towards or away from them, the light waves will come back either faster or slower, and they can use that change, that shift in frequency to calculate how fast you're going. Does that make sense? Now, what's interesting about this is that, if we go back to my little drawing here, in this scenario that I've given you here, this bug is traveling slower than the waves it's producing. And that's generally assumed what happens, when your car or the train is going slower than the sound it produces. Like, I don't know how fast that train's going, but do you think trains are going 700 miles per hour? Probably not. So when they pull their horns, they're going slower than the waves they're producing. But what's interesting is if you look at water waves don't tend to travel that fast. Let's assume that they travel at a speed of 10 meters per second. Well, a bug can't travel that fast, but what if it wasn't a bug? What if it was a boat? Can a boat travel faster than 10 meters per second, or 20 miles per hour? Yeah. Do boat waves look like this? Not really. What do boat waves look like? Well, let me explain. So if this bug, let's say, goes the same speed as the waves it's producing. So here's my bug. If it produces a wave right now, it'll end up looking like this. So this is what it looks like when the wave is the same speed as the bug. You all see that? They're all built up right on top of it. But if the bug or boat happens to go faster than the waves it produces, it's interesting because you still have a series of dots, from where it was, where it's going to be. But let's say the bug is here now. Well, essentially, it's going faster than the wave it created. So the wave it created just, a fraction of a second ago. I really hate this. The longer I do it, okay. There's my bug. So what happens is the wave it just made is actually centered back here, and so it makes a wave like this. And then this wave is centered back here, which looks like, say, this. And this one's centered back here, so it looks like this, and so on, so forth. So it ends up looking like this. Now, this doesn't look like anything in particular, does it? But here's the deal. What ends up happening is, do you see, I mentioned earlier, these lines all essentially look like crests. And so what ends up happening is the wave ends up looking like this. That should really be focused on the dot there. I did a poor job drawing. This is called a bow wave, or shock wave. It's where an object is traveling faster than the waves it produces. So for a better drawing, so it knows. So shock waves are produced when an object travels faster than the waves it produces. So here you can actually see two sets of pictures. So if you look at this picture with the planes, you'll notice their shock waves are almost flat. Okay? Whereas the drawing that I made, or this drawing up here, shows it as much more of a pointed angle. And that's because that's what will happen. The faster you're going, the greater difference in your speed versus the wave speed will change that angle. If they're basically the same, it's going to be almost flat, like in the picture there you see for the airplane. If you're going significantly faster, then it becomes more of a wedge shape. Now here's the deal. These shock waves are not, again, we're drawing in two dimensions here, and I mentioned that the waves of just that bug sitting there should look more like a sphere. These waves look like a cone. And so these shock waves occur as the waves are overlapping, and essentially you're getting a bunch of crests that just build up on top of each other. That's the shock wave. So here, there's a couple of videos which you can watch on your own about shock waves and the pistol shrimp. So the pistol shrimp and the mantis shrimp, their claws, they actually use their claws to stun prey. Think about like snapping your fingers. They kind of do something like that, but they don't have fingers. And they can stun prey with it. Like, basically, they close their claws so quickly that it creates a shock wave that will knock other animals unconscious. Because it turns out they close their claws so quickly, and keep in mind, they do this underwater, which is much more dense than air. Essentially, how quickly they close it, and when it slams shut like that, it creates a shock wave which is traveling faster than sound would travel underwater, which is stupid fast. And it creates this huge shock wave which can knock other animals unconscious, and then they eat them. It's fun because a lot of people will get mantis shrimps or pistol shrimps for like their aquarium, because it's a fun thing to watch them knock things unconscious. However, I do not recommend it, because if they happen to do it near the side of your aquarium, they will destroy the aquarium glass. It is that powerful, that if you want a pistol shrimp or a mantis shrimp, you have to get a specific type of glass that can withstand the pressure. So just a normal aquarium tank, which can withstand a lot of pressure to begin with, is not sufficient to house one of these animals. And if you don't believe me, well, you can always experiment with it. So shock waves. Here's another picture of a shock wave. Let's talk a little bit about sound waves in air. So we mentioned that when a sound wave travels through air, it travels about 340 meters per second, or about 760 miles per hour. But that depends on the air, okay? Literally, as the temperature of the air changes, the density of the air will change, and it will change the speed of the wave. Because, again, the speed of the wave depends on the medium. That's it. So we can say a couple of things about this. First of all, if you're talking about like airplanes and stuff like we have in the picture, if an airplane is traveling at the speed of sound, we call that Mach 1. So if a plane is traveling Mach 1, they're traveling at the speed of sound. If they're traveling Mach 2, they're traveling twice the speed of sound, and so forth. We could also say that the plane is sonic, supersonic, or subsonic. So if something is sonic, that means they are traveling at the speed of sound. Okay? So if something is supersonic, that means they're traveling faster than the speed of sound. If something is subsonic, well, they're traveling slower than the speed of sound. So for instance, it shows a picture of a plane here, but if you think about like bullets coming out of a gun, most bullets that come out of a gun are what we consider to be subsonic rounds, like especially those pistols. Just the bullets come out, 500, 600 miles per hour, but again, it's not 700 or 800 miles per hour or 1,000. So most bullets are subsonic. That means they're not traveling as fast as sound, but it is possible, especially in your higher caliber like sniper rifles, for them to actually fire a bullet that's traveling faster than the speed of sound. So that would be a supersonic thing. But whenever something travels faster than the speed of sound through the air, it creates a shock wave. And we have a special term for shock waves created in air when an object goes faster than the speed of sound. We call these things sonic booms. And the biggest misconception about a sonic boom is that people think that, oh, when you break through the sound barrier, that's the sound of a sonic boom. No. A sonic boom is that shock wave. Let's say you have this aircraft, and here you can kind of see the shock wave from the condensation occurring. This doesn't happen when the plane just breaks the sound barrier. This happens the entire time the plane is going faster than the speed of sound, because it's going to be constantly going faster than the waves it's producing. So a plane that goes faster than the speed of sound creates the shock wave that it drags along with it. And so if you hear a sonic boom, what that is, it's a shock wave getting drugged past your ear. But the plane is making the shock wave the whole time. And it will not stop making that until it stops going faster than the speed of sound. What's interesting is that anything, I think it makes sense for a plane to go faster than the sound it produces. Because, planes by themselves are very loud. And they're making a bunch of noise, and then they get going. Okay, finally we got to the point where it's going faster than the sound it produces. That makes sense for it to make this big old shock wave. But what's interesting is that anything at all, if you can get it going faster than the speed of sound, will create a shock wave, and therefore we'll have a sonic boom. because the tip of the whip is going faster than the speed of sound. How can that be? It's actually very simple. Earlier I mentioned the speed of a wave depends on the medium. If you've ever held a whip, the handle of the whip tends to be pretty thick, but the whip gets thinner as it goes towards the tip. And so what happens is when you put an energy into that wave, you put a little transverse wave into that whip, the energy will travel down the whip, but because the media is getting thinner, the wave will get faster. And if you give it enough energy for the wave to get to the tip of the whip, the tip will be going so fast that it will literally create a sonic boom. That is the crack of a whip. Which sounds remarkable until you just stop and just pause for a moment and think about this. Whips have a lot of history of whipping people and animals. And I'm sure you've seen movies of people getting whipped for one thing or another. And do the people in these movies seem to enjoy getting whipped? No. But here's the thing that I think a lot of people miss, because most people have never been whipped, so it's kind of hard to like, sympathize with this. But let me give you an example. Think about this. Let's say that this character in the movie gets whipped 10 times, and he doesn't enjoy it. Here's the deal. He is getting hit with an object traveling almost 800 miles per hour. As I mentioned earlier, there's a lot of bullets that don't travel that fast. That if you get hit with a whip, you're getting hit with something traveling over 700 miles per hour. That's ridiculous. Does that kind of make a little bit more sense of why a whip would hurt? I just think it's such a tragedy because, you see these things in the movies, and typically, the director or the writer is trying to express a particular thing. But if you've never, accidentally whipped yourself, or somebody else accidentally whipped you, you really don't understand it. Luckily, I've accidentally whipped myself, so I kind of understand it. But most people haven't, and it's really hard to empathize with this character if you don't know what that's going through. But like I said, keep in mind, if the whip is cracking, it's traveling at least 760 miles per hour, which is ridiculous because it's something you can hold in your hand and accelerate beyond the speed of sound. So that's it for the notes today. There are a couple of videos that you can look through.